Okay, so welcome to CQ seminar today. Let me happily introduce today's speaker, Professor Miguel Angel Sanchez Lozano from Valencia University. He is a world expert for high energy physics, in particular about phenomenological physics. So he will today talk about observable imprints of primordial gravitational waves on the CMB. Okay, please start.
Well, thank you very much. Thank you for the invitation to give this online seminar. And as you said, indeed, my specialty is elementary particle physics. So cosmology is somehow a kind of, appendix that, a field of interest, a recent interest, about 5 years that I am become interested in cosmology, also related to elementary particle physics, because of course they are not separated branches of physics. Everything is common. We have seen this is the lesson from history, and I have made this. I have developed this idea, but I have to say, of course, that I am not really an expert in cosmology. I am rather expert in particle physics. But anyway, I hope that I will tell you is interesting. And let's start just a kind of outreach, because we were told that even in very scientific talks, it's always interesting to give some kind of outreach introduction. So people who maybe are not especially involved in this field can have just a feeling of what's going on. So the idea, not really is well known, this is what I will say, is that you can have imprints from the past which will be useful to interpret the past, but also the evolution of the future. And this is the case, for instance, in the case of the fossils, the fossil records, which allows to a better understanding of the origin of life, the life evolution, and even after or before the era where this fossil was found or lived. So in the case of that we'll focus on is in the cosmic microwave background, which was produced, as you know, in about 400,000 years after the Big Bang. This is the standard, standard cosmology, where you had first, after the Big Bang, you have a period after the Planck epoch. You had a period where the universe grew at an incredible speed, and this is called the inflationary period. And when the universe just grew from the size of an atom to the size of an orange. I say orange because in Valencia we have many oranges, so a bit publicity about Valencian oranges. As a side effect. So after the recombination, there are a lot of epochs that I will not talk about. But what I would like to say is that this cosmic microwave background, which was released at time of the recombination where neutral atoms were formed, this cosmic microwave background at that time was not microwave. It was the temperature was about 3000 Kelvin, but because of the expansion of the universe, of course, it has cooled down. And this is what we see. But what we see is informing us not only about the later evolution of the universe after recombination happened, that, by the way, it didn't happen just in a moment, but took about 100,000 years. So recombination is not a single time in the cosmic time, but from the cosmic point of view, it can be taken just as a last scattering surface, but it is not. But I was saying that it informs not only about the subsequent evolution after recombination, but which are the recombination are the seeds of the present galaxies and other structures, large structures in the universe, but also about the earlier universe. And that's the point of my talk. What can we know about the very early universe by looking at recombination? In particular, I will focus on the possibility of detecting the imprints that primordial gravitational waves left on the cosmic microwave background, CMB. That's the objective of my talk. Again, just a review of some typical time scales that you can see here. The standard cosmology simply assumes that there is this time, it's very, very, very short, where the universe grew at such an incredible rate, exponentially. And later, after the reheating, well, it gave just its rate of expansion, of course, slowed down. And what I would like just to say is that the inflation solves essentially three problems which were in the cosmology before inflation was introduced by Alan Guth, Andre Linde, and others. And the three problems are the horizon, the flatness, and the monopole. The horizon, you know, is that if you assume that there is no inflation, then one could expect is that when you look at the sky, you should be not so uniform regarding the cosmic microwave background, regarding the temperature anisotropies. And to solve this problem is one of the reasons to introduce the inflationary scenario. Okay, so in this just a look at this is just a plot where we are plotting here the comoving scales. You divide naturally the comoving scale by the scaling factor A, then you get the corresponding physical states. For instance, imagine that we are defining kind of momentum K. K could belong to the Fourier expansion, for instance, of the 0-point quantum fluctuation of the initial inflaton field. And then K and 1 over K is a comoving quantity, physical quantity, comoving quantity. In order to get it, the physical one, you have to divide by A. In such a way, what you get is the wave function, the wave length, physical wavelength, which as you can see here on the bottom of this slide. And also let me very, very quickly distinguish between two types of fluctuations. On the one hand, you have the scalar, which corresponds to the usual fluctuation which is considered for a scalar field, like the inflaton is normally assumed to be. But also you can have tensor. The tensor would be attributed to primordial gravitational waves. So if you detect any influence of tensor perturbations in some physical observable, somehow you can claim that you are detecting primordial gravitational waves. Okay. So what's the starting point? I have these next two slides correspond to the main points that will be developed. It is a kind of abstract. So you know, the inflationary scenario, the primordial density and homogeneity are unavoidable because of quantum principles by the inflaton field. And these are seen at the seed of later primary temperature of the anisotropy of the CMB, and as well as the large scale structure, as I said, that I will not treat at all. And commonly, such temperature anisotropies are attributed to scalar modes, while tensor modes are expected really to contribute, but to a quite lesser extent, and therefore would be hardly distinguishable. Therefore, what common wisdom usually dictates is that in order to detect such primordial gravitational waves, one should count on polarization. One should look at polarization because there are modes of the polarization, B modes, which are only possible by generated by such primordial gravitational waves. And this is the main hope, and a lot of effort has been devoted and will be devoted. I remember that once there was this high energy physics conference in Valencia, the year 2014, and there was a big, I mean, you know, a big excitement because there was people claiming from BICEP that this was already seen. Alan Guth was there, and I remember taking a coffee with him, and he was really excited because this, of course, represented the Nobel Prize. But finally, this 5 sigma signal reduced to less than 3 sigma because there was other sources of B mode polarizations, and this is why finally this was just left. This possible, not left. I mean, such a measurement. Of course, there are efforts to see B modes polarization as maybe in the future even more. As I was saying, in this work, however, we will focus on the such expected small but maybe still observable effect of the tensor modes on the temperature correlation of the CMB. And we will concentrate at large angles. And this means low multipoles. And this means, in fact, the very early universe where such gravitational waves are expected to be produced. And I am aware the big uncertainties associated to such a region, angular region, big errors. There is the cosmic variance, of course. But let's just examine, let's just make an effort to see beyond prejudice. And the way that will be assessed in a more quantitative way is by using a parity statistic in order to see if such a odd parity, I mean, preference, which has been seen from Kobe, WMAP, and Planck in the multipole analysis of two-point correlation function, has something to do with gravitational waves. That's the main claim of this work. Okay, so let me also just comment that the lambda cold dark matter can be seen as a kind of phenomenological effective theory, like the standard model in particle physics. People think that it is not the ultimate truth, and something remains to be discovered. And in fact, there are a lot of discrepancies, anomalies, puzzles in cosmology, which put somehow in question the strict validity of the cosmological standard model. Okay, let's come, well, just the last sentence that our study, which is rather phenomenological, okay? There is a theoretical component, the kind of justification of the hypothesis to be introduced, but really, it is a phenomenological study based on the assumption that the field satisfy, I think the inflaton field, satisfy periodic and antiperiodic boundary conditions, not only periodic conditions, as can be expected as usual. And they will introduce this degree of parity breaking, which is needed to explain, for instance, the lack of large angle correlations, the odd parity preference, and as we will see, the possibility of detecting primordial gravitational waves. So again, a bit of a general introduction. Again, what's the typical size of the fluctuations of temperature seen at the CMB? It's of the order 10 to minus 5 Kelvin, so very small, but they are. They are there. So something has to be done, because if nothing is done, what should be expected from this view of the celestial sphere is that, well, the regions, more or less homogeneous regions, should have the size of the moon, more or less. And of the order of 2 degrees. And the moon, I think, is smaller than that, but of the order. Okay? About 1-2 degrees. This is what would be expected that this picture tries just to show up. However, what we see is really a uniformity, but not total uniformity. And that's what we will try to analyze. And there are 2 ways to analyze, as far as I know, from the point of what I am saying, of the angular distribution. I'm talking about specifically about the angular distribution of the CMB, okay? And to do that, there are basically 2 approaches. One approach is by using the so-called angular power momentum, which you can see represented to the right by this curve, where you can see the acoustic peaks, so well reproduced. So it is a great success of the standard cosmological model. It is really impressive. However, if you look just on the left side of this plot, you will see that there is a kind of, to say, some deviations. Of course, there are big errors, but here they are. And this can be also studied by using the correlation function. The correlation function is something which is, in principle, equivalent to the power spectrum, in principle. And the correlation function is defined as you see here. It's an average value of the temperature differences along 2 different directions in the sky, defined by angular theta, which takes value between 0 and pi, between 0 and 180 degrees. Okay, so that's the function C, the function of theta, this angle between the 2 directions of the sky, and this can be developed taking the Legend polynomials as a basis, as usual. Okay, this is the usual way that this is expanded. Okay, and each L, which by the way starts at L equal 2, because the monopole is a kind of constant and not of interest for this study, and the dipole term is removed because there is a big contamination by the dipole due to the motion of the Earth. So it is usual that in all analysis, this dipole is simply removed from data and therefore removed from the corresponding theoretical analysis. So that's the function from L equal 2 up to infinity. And of course, infinity is just a number. I mean, it is not a number, it is infinity. But we will put the right, value in order that it has no influence, the upper limit of this sum. Well, you can see here, by the way, that this L, in the case, can go up to several thousand. But okay. So also there is a relationship between L and the angle. I mean, like a kind of mean values. For instance, L equal to, say, 200 corresponds to about 1 degree. The correspondence is that 180 divided by L is the typical angle, but it does not mean that a particular value of L of the polynomial affects all the values for any angle. That's the difference between this angular power spectrum and the study of the correlation function, where you have a rather holistic view of the influence of any L over the whole range of angles. So assuming at this moment that the spectral index of the power momentum is 1, which is what it is expected from a poor inflationary model, as was one of the main predictions, then these CLs, such coefficients of each polynomial, is given by a very simple expression. This simple expression is given there, and it is related to the Sachs-Wolf effect, which mainly means that the density inhomogeneities are translated to perturbation of the metric, and finally this ends up with temperature anisotropies. Okay, and it is, well, this is what we will do, and it is expected to be dominant, this Sachs-Wolf effect at the small L, let's say less than 30, less than 20, it's just a number. Above 30, for sure, it's not the main, the dominant mechanism. There are other mechanisms like integrated Sachs-Wolf that I will not talk, because what we are going is to just to concentrate on this region. You see that this red curve, which has just growing at low L, the fact it is growing and it deviates for a plateau is due to this integrated Sachs-Wolf effect. Okay, but let me just point out that the net effect is just a small, slight increase of the plateau, nothing else. But not this structure of a C-tooth that you can almost guess. Let's come to the next. And I would like the next to just to convince you, if you are not already convinced, naturally, that there are several anomalies from COVID, WMAP, and Planck, in particular, are related to correlations at large angle. So what is expected from the usual lambda Goddard matter model is the curve that you are looking at. By the way, excuse me, can you see my pointer as I move it? Do you see it?
Yeah, I can see.
Okay, because it's very, very not easily seen, but okay. So if you see it, good. So I am now just pointing at this curve, which corresponds to the expected. And you can see that there are positive correlations. Positive correlations means, as all correlations means, that if you have a point of the celestial sphere with a given temperature, you will have in the other point another temperature which goes in the same direction. Positive, it is slightly larger than the mean value, the average value, it will be also larger. It is smaller, positive, because it is a product. So you have the same sign, you will get a positive correlation. And this is something which is there. And you can see, even seen from WMAP, that it is relatively safe to say that it is not within what expected, what's seen by experiment, even with errors. So you have, on the one hand, that what could be expected, correlations everywhere, positive, negative. It's not so in the case of what has been observed. Above 60, 80 degrees, there are rather zero correlations. And now I just come to the right of this slide, and this is the same, but using one of the sets of Planck 2015 dataset. And you see the same behavior. And you see that there is a region which is just signaled by this arrow, blue arrow, where you see that as it repeats the same trend of not positive but rather negative correlations. And more than, so we have a kind of zero correlations above, let's say, 60, 70 degrees, but at the end, above, let's say, 150 degrees, and what you get is just negative correlations. And let's understand what's going on. How can we interpret this in terms of the two contributions to this curve from the legend expansion? And here you can see that I have decomposed the function in the even and odd contributions. That's, of course, absolutely possible. But let me just remark that the two different behaviors of the two pieces. The even piece is even around 90 degrees. If you, instead of using the angle, you use the cosine the angle between -1 and 1, you would get about 0, the origin, which is 90 degrees. So what you get is what expected for an even function. And for another function, you have, of course, this symmetry, anti-symmetry, in the sense that you get negative values, what you get positive values. So immediately you see that for small angles, there is a kind of constructed contribution because both have the same sign. So in order to reproduce the quick rise of the function is easy. It's easy. But at large angles, above, let's say, 150, I was saying, degrees, there is a delicate balance. So if you alter not so much the weights, CL, corresponding to the odd, if you alter the CL corresponding to the even, okay, you may have, if you change both of them or at a small angle, you can have some changes, but it is not dramatic. But on the right, it could be rather dramatic in the sense that the variation could be relevant even for not so big variation of CL. That's the main point, one of the main observations of this talk, okay? Also, let me point out that there is a very bad fit corresponding to the correlation function at experimental points. In this case, it's the last Planck 2018 dataset, because apparently there is a downward tail, and you can see from the side, from the right side, that this not should but must be attributed because of mathematics to the term, to the odd term, which is overcoming the even one. That's poor mathematics. So if you want to get this downward test, if you believe this is not a statistical fluke, in such a case, you have to modify the CL accordingly to weight more and more the odd contribution with respect to the even. And that's also the object of this work. So to do that, there are several attempts in literature. For instance, Paolo Cea, the University of Bari, in the ellipsoidal universe, where he, by changing the metrics, he is able to change the quadrupole. And in such a way, he somehow corrects this behavior at large angle. Another approach was initiated by Fulvio Melia at the University of Arizona, and Martín López Corredoira at the Instituto Astrofísico de Canarias, where in a pioneer work, they introduced a cutoff in the power spectrum, somehow by hand, motivated phenomenologically. And also, I have to say that they use not a standard cosmological model. They use the so-called RH equals CT universe, a linearly expanding universe without inflation. Of course, this is completely outside the mainstream. But in any event, they introduce this K-mean within this universe, which is not, the most favorite among cosmologists. In any way, let me just point out what the effect of the introduction of K-mean, which corresponds to the introduction of a lower cutoff in this integral that we saw, is just coming from this plateau expectation, okay, at a small L. So this G is the Bessel, spherical Bessel function. So when one modifies this, then you modify as well this dependence of CL that just before had this dependence because of the plateau. Later, Fulvio, Martin, Nicolas, and myself, we extended the study not only this linearly expanding universe, but for a more conventional universe. And this is the curve you can see here. Okay, where we were able, by introducing again, reintroducing, so reanalyzing, because the gas de Melia, the study was done with previous Planck data, not the last one. This is with the last Planck data, and also using, I mean, not necessarily this linearly expanding universe. And this is what we got, which is not bad, I think. You see that we are able, by just, I mean, this is fine-tuning somehow. No, fine-tuning is not the right word, but just tuning, so tuning. By tuning the value of this minimal u, we are able to modify the CL in order that this balance between the odd and even contribution is altered enough in order to get zero correlation. But you can see that this tail, downward tail, is not reproduced at all because it didn't want at that moment. Okay. Why? If we believe that this tail is not a fluke, if we believe that it is really something which has a cosmological origin, something has to be done. And this something to be done should be related to parity imbalance. So let's introduce a parity asymmetry statistic, because after all, we have seen that at this large region, angular region, there is a parity breaking in order that the odd terms dominate over the even ones. So in the literature, there is introduced this statistic that mainly is one if there is a perfect symmetry between the parity contributions. Okay, and this is what it is just hinted on the left side of the slide. This one is what it is expected if we do nothing and we use this, I mean, the Sachs-Wolf effect, nothing else. But this is what is obtained experimentally, observationally, from Planck data. And you can see this as a function of L. L max in the summation comes from 3 to a maximum value. It tends to unity, of course, because at large L, one should recover the good region where everything is perfect. I mean, the acoustic peaks, etc. But we are not focusing there. We are leaving this region. We are studying the small region. Okay, I'm sorry, the small L region, the large angle region, and you see that well, the deviation is enormous. So by introducing this, as I was saying, this infrared cutoff, just one single infrared cutoff, what you get it is, well, now the disagreement is not so bad. There is an improvement. We are able, especially at low L, to come closer to what expected. In particular, the quadrupole, which would be mainly dominating the first point, an orange point, comes very close to what's really seen. But we are not yet satisfactory. It's not yet satisfactory. So something else has been done. So the point is really our universe odd in all senses, a particular parity odd. And this is why somehow will repeat a bit what I said before, but in a more general context. So the point is that this is the same definition. Let me just point out here to stress that the CL are determined. I mean, we are using a particular model. This is as we were saying, we are using the Sachs-Wolf effect modified, and with a normalization, which is free. So actually we have two parameters, the normalization, and we have also this lower cutoff. But anything else is fixed. I mean, it is not a completely free fit at all. So let me just flash you what is expected. I am plotting here both what is expected by a fit of data, the best fit, best chi-square fit. You get these positive correlations. This the left side is more or less correct because it is not so good, but there is no delicate balance, I was saying, and this is what I said. I am just repeating. So again, I repeat what we got. Just a single cutoff was introduced in the scalar. Let me just remark that it is scalar perturbations. So as I was saying before, the main effect is to reduce the quadrupole contribution, like in an ellipsoidal universe, as Paolo Cea has suggested as a possibility of a different universe, of course, breaking isotropy stemming from the cosmological principle at the big scales. But now what's the point? The main point is the introduction not of one but two. In order to introduce two infrared cutoffs, then we need a physical argument. And the physical argument is based on boundary conditions to be satisfied by at the moment of the release. And it is based on causality. I will notice this RH is the Hubble radius. The idea basically, and I will not have no time, and it will be in our paper, it is explained in my paper, the universe, published in Universe is explained in detail, is that when you assume that two boundary conditions have to be satisfied, and this can be required, for instance, if your field, fundamental field, is a fermionic field, so you have actually two conditions, two boundary conditions. What you get basically in the expansion, Fourier expansion, is that you have either integers or half integers. Let me point out also that the integers you can convert quickly into even numbers, just multiplying by 2 and dividing by 2. And you change the scale, but you get, I mean, odd numbers. And the half integers, what you get is odd numbers. So even odd numbers is contained, comes directly from the assumption of having periodic and antiperiodic boundary conditions. And the factor 2 turns out immediately as a consequence of this hypothesis of the two periodic conditions. But the key point is to associate the two boundary conditions to these two sets of polynomials. The odd polynomials, which corresponds, they can be expressed mathematically. That's a textbook. Well, it is not exactly a textbook, but you can work this and to see that indeed this the odd polynomials can be written in terms of half integer angles, while the even polynomials are written in terms of integer angles. So when this decomposition that we saw that corresponds to the two different behaviors whose balance leads or not to parity, odd, parity, even dominance, if you want, since in Valencia we love music, one can think of a kind of a cosmic duetto, because you can think there are instruments like the clarinet that essentially only emit because of the construction of, of the disposal of the tube. You have only half integers notes, while in the case of the oboe, for instance, you have integers. And well, you can think it is that there are two instruments playing at the same time when this cosmic background was released, and the corresponding coefficient for each polynomial is given by these two cutoffs. These cutoff in the ratio equal to 2 because they are fermionic. Kind of G minus 2 question.
Sorry, sorry, I have a question. If you put u mean even equal to u mean odd, you recover an even situation. So u mean even and u mean odd need to be different.
Yes, if I recover, if you see, if I put the same u, this is what you mean, okay? Instead of factor
So
2.
just to understand, you mean even
yes,
you
sure.
two, you mean odd. Okay, sorry.
No, I still, sorry, still there is no, I mean, there is no, it is a dominance of odd, but no, not enough. If we put a 0 here, instead of between 0 and infinity, it would be the standard
So
cosmological model.
the standard cosmology is 0. Okay, sorry.
Yes.
Okay.
If you put just one, what you get is an improvement. There is a parity dominance, but not enough because the downward tail is not reproduced. So what
So
we
the factor of 2 is put by hand, or so what
it is not so by hand. It is simply because of this relation, and this is because you have in one case, imagine that this is a kind of string theory. You have to make the circle of 2 pi r h, and in the other condition you have to do it twice. So, and if this length scale is twice, then this means that the corresponding momentum is half or twice. It depends how you see it. So what I mean is that this factor 2 is not something which is put by hand, but coming from this assumption of these two boundary conditions.
Okay.
And also I have to say that in my phenomenological study, prior to that, the factor 2 was favored. So I was led to this factor 2. This made me think why this factor 2, and it was a posteriori that I thought it was due to these two different periodic conditions. So there is the factor 2 is not arbitrary because phenomenologically we are led to that in order to get the best chi-square fit, and on the other hand it has this theoretical justification. It's actually a factor 2 because you have this condition which is coming from somehow string theory. So here is my last paper published in Universe, and you can have a look at the two effects. I mean, either on the correlation function that you get a relatively good fit, and also you can see that the curve corresponding to the statistic is approaching closer to the expected, the seen values by Planck, but not yet perfect. But we have made another step forward in the agreement. And now that's come the main point of the talk, that my talk is finishing anyway. What if we include primordial gravitational waves? And you have, again, I come back to the previous one to compare. This is the correlation function. You see that the tail is well reproduced, okay? Downward tail, but there is a region here. Maybe also it is a statistic, because depending on the data set, this was a bit lower. The big errors, which are not plotted here, of course. But maybe the right curve, which is measuring this degree of the deviation from positive correlations, you see that indeed there is an improvement. But here the improvement is I would say, very significant. And what we have done is to include tensor modes. Tensor modes, you may think, well, if we introduce more parameters, everything is possible, of course. But we are not introducing so many parameters. In fact, we are introducing just one more, and even it is constrained, because first of all, the new CL which are added to the other ones for L smaller than 30 are given by a theoretical expression that you can find in Mukhanov textbook. This is a well-known expression, okay? In the Mukhanov, it is 0. It has been modified. Now we have again even odd, but for tensor modes. With a factor 2. Okay. So this is what we get. And what we get, I would say, is extremely good because the agreement now is very good. You can have here, look, I hope that it's possible to see it. Well, the upper figure, you remember, was just unity. So it's just a straight line, unity. And this is how we are improving the fit, this fit. This fit is simultaneous to the other fit, to the fit of the correlation function. You see, simultaneous means that we are looking for the best chi-square fit for both of them, with the same parameters, obviously. And you see that, well, this is what I said. There is a first attempt with one single cutoff, a scalar cutoff. Okay, good. With a double cutoff, we are approaching more this, but with the tensor modes, we really get, I would say, a spectacular coincidence. And well, what about the parameters of which are, this is a fit. So what we are getting, for instance, the ratio between the CLT and CLS, which is, of course, the corresponding coefficients of the polynomials for the tensor modes with respect to the scalar modes. And this is, the expression is well known in literature. It is about 4 pi, the epsilon parameter in the inflationary models. And what we get experimentally is about 5%. 5%. And with the 5%, we are able to bring into much better agreement the curve I showed you before. This corresponds to this epsilon, if I have not made a mistake, because we are still working on this. Something active, it is not finished. This means a spectral index, which is about 0.976, which is, I think, within current limits. And the NT, the R a bit high. I had to think about that. So, and please think that these are obtained from fits, independent fits. I mean, independent in the sense that nothing related to NS. We made the hypothesis that NS was equal to 1, of course, but okay. Afterwards, we see that actually the value should be this. And what's the theoretical motivation for this ratio 2? So one can have fermionic fundamental fields. This would correspond to an inflaton field, which is not real fundamental itself, but it's a composite and it's made of 2 fermionic more fundamental fields. Let me point out that, well, this is not absurd, because there are people who think that the fundamental fields are really fermionic, not scalar. Also, imagine the Higgs particle, the Higgs boson. There are models trying to explain this as a composite of top at the top, fermionic particles. Okay, so it is not so absurd to think that there are models in the literature about the possibility that you have a composite field, in particular made of fermionic subfields, which they should satisfy the boundary conditions. And the boundary conditions, periodic and antiperiodic, come naturally for a fermionic field. They must be there, in fact. But there is not the only way. You can also think of extra dimensions. So one can somehow forget about the Dirac fields and to think we have extra dimension, and you can generate periodic and antiperiodic boundary condition also with a scalar field, but introducing extra dimension, at least one extra dimension in the Kaluza-Klein model scenario. always keeping this relation of the even is twice the odd. And the conclusions come now. The current anomalies, just and tensions are there. The Hubble constant, which depends on the way it's measured. So there are a lot of, unfortunately, I would say, because when there's something which doesn't work, normally leads to something even more interesting. So in our approach, as I was saying, I have been saying so many times, there is this odd-parity preference that we accept as something which is not statistical, but of cosmological origin, thereby breaking, to some extent, isotropy, which comes because isotropy would not allow you to have such a parity imbalance. And this has been observed by all three. So we introduce two effective infrared cutoffs in such a way that the range of variation. I have generated 100 mock universes. I have obtained this the variation for the corresponding U, so they are not exact values. I mean, but the ratio was always fixed to be equal to 2, right? Sorry. And there's this phenomenological result can be motivated or justified by such periodic and antiperiodic boundary conditions. And what is more important, in my opinion, well, everything is important, but once the contribution of primordial gravitational waves is incorporated into the analysis of the temperature correlations, no polarization, then the fits of both the correlation function and this parity statistic both improve significantly and at the same time. But naturally, having said that, polarization is also, of course, the smoking gun. And last but not least remark. Well, I have divided this Q in regions or areas of influence. So, for instance, a small L, which here's the quadrupole, this would be mainly scalar modes which are dominating. And the tensor modes are not affecting so much this region. The region where really the tensor modes contribute mainly, and therefore bringing into a better agreement the curve, the orange curve with the experimental points which were obtained using different masks from raw data to remove foregrounds, etc. I'm not an expert there. I have just taken from literature using two different masks in order to be, but they're not so different. Our somehow predicted, see the word predicted, but obtained curve matches it very well. And that's all. Thank you very much.
Oh, thank you so much, Professor Miguel Angel Sanchez Lozano. Any questions?
I have a question about this odd-parity preference. At the very beginning of the talk, you just showed that there is a very delicate balance between even and odd. Yeah, a large cancellation, right? So if the measured quantity, the measured value implies which level of cancellation. So these two numbers need to cancel at which level in order to give the correct number, the observed number, let's say.
Well, there is no unique number in the sense to measure, determine which is the deviation from the dominance of even over odd. So there are authors, for instance, I have not done this, they make the integral from 90 degrees up to 180 degrees, the integral, and the area is a measure of the degree of parity violation, because it is 0, no, I mean, there is no dominance. Positive, you have a excess of positive correlation. Negative, the opposite. And this is, well, I was thinking to include this in my analysis, but instead of having just a number, you know, called S1/2, normally in the literature, this is integral, which well, several years ago was used to determine this disagreement between what expected and what seen. In my case, this is somehow distributed along a curve. You can see this can be, in order to reproduce all this downward tail, or if you prefer to use the statistic, because after all, if you got something like 0, what you would get is something which is something like that, okay? So what I mean is that it is not concentrated on one single number, but rather, well, the single number is the fit, is the chi-square, the fit, the reduced chi-square. So the reduced chi-square is measuring the degree of the disagreement of your orange curve, which is what has been obtained using the fit. I mean, this is getting this fit corresponds to the orange points here. So the chi-square is telling you how good is your fit with respect to especially to the tail, because at the end you see that it approaches unity very well. So, and this means large L means small angle. So at small angles, everything goes well, but this is what could be, must be, because we will not spoil the very good the very good shape of the curve for the acoustic peaks and so on. Therefore, we are concentrating in this region. And if I understood your question, there is not a single number to determine that, but the fit of the curve this and the fit of the other two, which are related. And well, the number is the chi-square. Since we got at the end a chi-square of the order less than unity, about unity or smaller, we think that we have succeeded in approaching the theoretical curve to the experimental points.
No, what I was thinking was simply that if you have a result that is the sum of even and odd, your theoretical model, if you change a little bit the difference between, so if you change separately even and odd by a very small amount, like 10 to minus 5, 10 to minus 6, but their difference can change by 100% because there is a large cancellation. So I was just wondering if the interpretation, the fit is very sensitive to how you modify left odd versus even.
Right.
Sensitivity of the fit.
The sensitivity of the fit. Well, this can be seen at the end of my last, one of my last slides, where you have here an average value of the CL. This is, you can compare because you have modified the CL by using a different expression, and you see that indeed this corresponds to a relatively large change, for instance, the spectral index, or the R, which is the ratio between the amplitudes of the tensor to the scalar power spectra. And what I mean is that in this case, this is of the 5%, because you have this C-tooth ISO behavior, but averaging, you get about 5% variation. So with a 5% variation of the C, what you get is this change. I mean, from here to here. So it is quite sensitive. Of the order of few percent, you get changes which are visible, observable. But not 10 to minus 5. The change is larger than this. When you are modifying the U the U cut, I mean, this is because when, for instance, let me see here, you have this dependence on U. So the modification of U mean has really impact about 10%, so to speak, but for small L. At large L, practically doesn't change. So at small L, when you modify U, instead of 0, you point 4.5. What you get is this about 10%, but it is first 10%, 5%, 2%, 0.1%. So that's the way it changes as L is changing. Only the few L are really affected, to a 10% level. And this has this sensitivity that we have seen. This is why the first scalar modes, I come again to the last one. This is because the scalar modes with the U cut is affecting relatively strongly, but it is the first ones. Really, the C2, for instance, is more than 10%. It is largely affected. But as the L is increasing because of the shape of the spherical Bessel function, then the influence gets smaller and smaller. Therefore, as a kind of mean sensitivity from 2 up to 10, the sensitivity for scalar modes is of the order of 5%, I was saying. Much larger for the quadrupole, much smaller for large L, approaching L, and almost negligible for L larger than 10. And then you have to resort to something different. That's the point. If we want to fall this curve, orange curve, down in order to get experimental points, something else has to be done. And this is attributed to the tensor modes, which are acting precisely on this region. And above the region, again, the effect fade away. They do not contribute for larger. They are just increasing slowly because this is a statistic which is just a sum. You are not totally forgotten what you had before, but as you are getting more and more L, then the imbalance is diluted, and this is why asymptotically you should get unity. But it's a small L where the effect really appears, and the sensitivity on U is extremely large for the quadrupole, but not so, and it is decreasing quickly as L increases. And it's a mathematical reason because of the shape of the G function.
For the questions. Okay, if there is no question, then let's thank Professor Sanchez Lozano. Yeah, thank you so much.
Yeah. Thank you very much for inviting me.
Thank you.
Bye-bye. Yes.
Wait a moment. Since there are no other questions, maybe I can take the opportunity to ask you.
Please go ahead.
Another thing about the error bars at very low L. Because everything is based on a chi-square, but the chi-square depends on the error bars. So can we trust the statistical error at very small multiples?
You are right that this is a delicate, weak point, because it is true. For instance, I can come here where we see just what are the size of the I think 2 sigma error for the non-negligible, and this is the typical size of the errors you can see here. So it is true that at large angle, small l, there is big uncertainties. But this was taken into account to obtain the chi-square. But it is true that, the chi-square reduced, because in the case of the reduced, it is divided by the number of degrees of freedom in order to get this chi-square reduced. And it is true that there the errors are big. I cannot hide this. But nevertheless, along the curve, you see that, the tendency beyond the individual errors suggests that indeed this new contribution puts in a better agreement, overall agreement. But I have taken into account the errors when I say chi-square near unity, it is taking into account the error bars obtained from literature.
Yeah, so the point is how these error bars in the literature are obtained and how we can trust them, if they are robust at very small L. This is especially the statistical error, because the cosmic variance, this is the problem that
is there. Yes, it is impossible to avoid.
it is impossible to avoid. So how is it? I don't know. When you look at the experimental bars, let's say experimental points, there are some error bars at L equal to 2, for instance, L equal to 1, L equal to 2, L equal to 3. And honestly, personally, I don't know how they are calculated.
For instance, here, okay.
Yeah, these error bars.
Yeah.
These
error bars were incorporated in my analysis somehow. Okay.
Yeah. So the question is whether these error bars are.
Yeah. Well, in this case, I trust the.
Yeah. One has to take as a face value, but the moment that because people usually don't care much about that part, but the moment that you focus on that part, then one should understand also if these error bars are reliable and how they are obtained, because you have very few data. So you are observing very large scales, so you cannot average over the sky like in the other cases.
I think you are exactly saying the main point, because in any claim, one has to show something, to demonstrate that, of course, this is a statistical study. It is a phenomenological study where statistics is playing a role. And you are definitely right that it plays. But this is what we have. Let me point out that in case of polarization, so I was saying in Valencia, there was such a big excitement. It was over 5 sigmas. And finally, and it was smaller than that. I mean, because when one's taking into account the galactic dust, I think it was another source of beam mode polarization. So 5 sigmas deviation was very optimistic, too optimistic. Yeah. And so the estimate of errors and uncertainties is very important. So what I am showing you, it is not an evidence, but a hint.
Yeah.
It is a hint that
so
indeed
it's an indication also to the experimentalist to focus more on that part.
Exactly. That's exactly. The paper we're writing, this is exactly our last statement. That it is
so we should pay more attention to the low
Exactly. That's the point. That's the point. Because normally that's the point. Normally it has been just not considered because of what you are saying, because of the big errors. But there is one thing: when you see you have a small error, big error, but the tendency of the set of points is steady, you can even draw conclusions in spite of the big errors. This is what actually we are doing, because the tendency is clear that the improvement goes in the right direction in spite of the errors. It is true that I didn't represent the errors, because then I took this curve anyway, the blue curve from literature as it is, okay? I didn't do anything else. And well, this is what I got. It is an improvement. And this improvement is, I would say, quite significant. But if you put error bars there, although it is a partial cancellation, because you have ratios of CL, okay? So there are some partial cancellations. But it is true that maybe within big 2 sigma, it would not be significant enough to make any claim of discovery. We are not doing that, but simply calling the attention of the community to this region, because if we include new contributions, the agreement improves. That's our message.
Okay, thank you. Then enjoy Friday in Spain.
Thank you very much. Thank you very much.
Okay.
I hope, Stefano,
Adiós.
see you. Hasta luego. See you soon. Bye, Valencia again.